The d block elements in the periodic table are called the transition metals, and they all have this properties of being able to form different ions with a different oxidation state. They can have a partially filled the subshell. The scandium and zinc, the two elements which are at the beginning and the end of the 3D block, they are not considered as transition metals because they only have one oxidation state. So what are the properties of transition metals? They have four properties which we are going to talk about in the discussion of the transition metal. The first one is having a variable oxidation state and then being able to form colored ions. They act as catalysts and they form complex ions. So let's start by talking about the complex ions. So what are the complex ions? Complex ions formed of a central metal ion surrounded by ligand. These ligands will donate lone pair of electrons to form coordinate bonds or dative covalent bonds. So according to how many of the ligands can surround the central atom, the shape of the complex ion will change. So we have four different shapes of the complex ion. The first one, when we have small ligands like ammonia or water, each of these will have lone pair of electrons either on the nitrogen or the oxygen, and they can actually donate these lone pair of electrons and form a coordinate bond or dative covalent bond with the central atom. Then we can have up to 6 of these small ligands around the central atom, and the shape will be octahedral. When the shape is octahedral, the bond angle here is going to be 90. So some examples of that, when we have the ferric ion or the iron 3 plus ion, and it's surrounded by 6 molecules of water. Each of these molecules will give you a coordinate bond with the central ion, and that will give you the complex, and this complex will have a charge. The charge here will equal the total charges of all of the molecules making that complex, or all of the particles making that complex. So we have the iron has 3 plus, because it's an ion, 3 plus charge. The water molecules, they are neutral, they don't have a charge, so the total charge of the complex ion here will be 3 plus. And then we have something like copper. We could have more than one of these ligands surrounding the central ion. So copper could have up to 4 of the ammonia and 2 of the water surrounding the copper, and that will give us this complex ion. Again, it's going to be octahedral because in total there are 6 of the ligands surrounding the central ion. The charge here will be 2 plus because this is the charge of the copper and all of the ligands are neutral. If we have something like chloride, chloride also can act as a ligand, and chloride here is an ion. It's bigger in size, and the maximum number of chloride that can surround a central atom or a central ion is 4. So the maximum number of the ligands around the central ion will be 4, and the shape here will be tetrahedral, and the bond angle will be 109. Some examples of these is the copper surrounded by 4 of the chloride, so copper Cl4, and the charge here again will depend on the charge of these ions. So the copper is 2 plus, and we have 4 of the chloride, each with 1 minus, so in total there are 4 minus, so the final charge will be 2 minus for that complex ion. And then we have something like copal chloride. It's the same as well, 4 of the chloride surrounding the cobalt ion, and the cobalt is 2 plus, 4 of the chloride, each with 1 minus, so in total 2 minus. Also, we could have 4 of the ligands surrounding a central atom or a central ion, and we end up with a shape, a square planar. And this is an exception. It's different from the tetrahedral, and you need to know that exception, which is the cisplatin or the platinum. So when you have platinum and it's surrounded by 4 ligands, 2 of these are chloride ion and 2 of these are ammonia, and you end up with this complex ion, and the shape of it that is square planar rather than tetrahedral, and the bond angle here is 90. There are four ligands. Sometimes you could have maximum of two ligands surrounding the central ion, like silver with two of the ammonia. In this case, the shape is going to be linear because there are only two ligands surrounding the central ion, and then also the charge will depend on the charge of the different components of this complex. So the silver is 1 plus and the two ammonia are neutral. So in total, there will be 1 plus. The types of ligands. We have two different types of ligands. We can either have a monodentate ligand. A monodentate means a ligand that can only donate one lone pair of electrons to form only one coordinate bonds. Examples of these is water, ammonia, and chloride. And then we have the bidentate or the multidentate. So bidentate ligands means that they can donate two different lone pair of electrons to form two different covalent bonds or coordinate bonds with the central atoms. Examples of these are the ethane 1,2-diene, like this one. So we have two amino groups here with two nitrogen. Each of these nitrogen can donate the two electrons in a coordinate bond and will form a coordinate bond or dative covalent bond with the central atom. That means it's bidentate. And also we have the ethane diuate, which is two carboxylic acid basically linked to each other, or carboxylate, and the charge of this is 2 minus. The two oxygens with the negative charge, each of these can donate the lone pair of electrons and can make two dative covalent bonds. And then we have the multidentate one, like ADTA or EDTA. This is the structure of the EDTA, which has two nitrogens here and has four of the oxygens with a negative charge. All of these six atoms can donate lone pair of electrons to form six different dative covalent bonds with the same central atom. So this is called a multidentate. Some of the examples, or sometimes in the exam, they ask you to draw the complex of a certain ion with one of the bidentate ligands. So for example, to draw something like that, we have here a central ion of iron 3 plus, and we have three of the ethane diuate ions. Each of these will make a two dative covalent bonds with the central ion, as you can see. And in total, the three molecules that are surrounding the ion, because the maximum will be six dative covalent bonds surrounding the central ion. So the three will have a total charge of 6 minus, because each of these will have two minus charge. And we have the iron has 3 plus, so the complex ion itself has a total charge of 3 minus. The displacement or replacement of the monodentate ligand with a multidentate or a bidentate ligand is called chelation. So chelation is when a bidentate or multidentate ligand substitute or replaces a monodentate ligand around a central around an ion. And now the new complex that is formed will be more stable. Why would it be more stable? It will be more stable because there will be more particles produced at the end, because you are replacing six particles or six ligands with either three in case of bidentate or with only one in case of the multidentate, especially if it has six different, can make up to six different dative covalent bond like EDTA. In this case, if you have as a product a larger number or higher number of particles, that means the system will be more stable because the entropy will increase. So when we talked about the entropy, the degree of randomness or the disorder, it increases with the increase of the number of particles. So basically, if you say you are replacing the six water molecules surrounding an iron with ADTA or with EDTA, then you are moving from having two particles on the left-hand side into having seven, because there is now the complex ion and six of the water molecule. So there will be an increase in the entropy, or the entropy change will be more positive. So this is why it's more stable. Isomerism of the complex ions. So complex ions can form different types of isomers. The first one is the optical isomers, and optical isomers can be seen in case of octahedral complexes when they have three bidentate ligands. So something like chromium with three of the ethane diamine ligands. So as you can see here, you can have non-superimposable mirror image of these two to give you the optical isomers. So this is a mirror line, and these are the two complex ions. So these are optical isomers. And then we can have the cis and trans. There are two cases for the cis and trans isomers. The first one is with octahedral complexes when they have four monodentate ligands of one type and two monodentate ligands of a different type. In this case, we can have either a trans, the isomer, where the two ligands, which are the odd ones or the different ones, are opposite to each other. Can you see the cobalt one, which has four of the water and two of the chlorine? The two chlorines here are opposite to each other, so this is the trans isomer. And then we can also have the cis. In this case, the two odd ones will be next to each other. So this is the cis and this is the trans. Another one is the one that we can see in the square planar complexes when it has two pairs of ligands. So we have two different ligands. Each of these will have will have a pair of the same type. So something like platinum, platin, cis-platin, and trans-platin. So cis-platin, as you can see, there are two of the chlorine and two of the ammonia, or two of the chloride and two of the ammonia. And then if the two chlorines are, or the two similar ligands are next to each other, then it's going to be the cis isomers. And if the two, which are one of the main properties of the transition metals is the ability to form colored ions. So why the transition metal are able to do that? So the colored ions or the colored complex come from the d electron transition. So when they have ligands surrounding them, the ligand can split the D sub level into two energy levels. And then electrons can gain energy from by absorption of light from the visible region, and then this will cause the excitation of the electrons from an energy level to another energy level. The color that you see is the complementary color, or the part of the light that was not absorbed. So this is called the complementary color. So the color of the complex of the transition metal will depend on four things. The first thing is the metal ion itself. So depending on which transition metal we are using. The second one is the oxidation state of that metal ion. So you could be using the same metal ion, but with different oxidation state, and that will give you different colors. And then the ligands, so different ligands will give you different colors. And finally, the coordination number, whether you're gonna have two, four, or six ligands surrounding your central atom. So you can change, if you use the same ligand, you can change the color of the complex if there is a change in the oxidation state, or if there is a change in the ligand used, or if there is a change in the coordination number. And this is one of the typical questions in paper one. They could ask you, how can you change the color of the colored complex? We can use spectroscopy to find the concentration of the transition metals. So transition metal ions usually form these colored solution due to the d electron transition. The amount of energy that an electron absorb in order to actually be excited from one level to another can be calculated. So the delta E, or this energy that was absorbed, equal the Planck constant times the frequency, and the frequency is in second minus 1 on in hertz. We can also find it by the Planck constant times the speed of light divided by the wavelengths of the light that was absorbed. So the wavelength is usually, we find it in meter, but it's usually provided to you in the question in nanometer. In order to convert from nanometer to meter, you have to divide by 10 to the power of 9, or multiply by 10 to the power of minus 9. So the intensity of the color produced is related to the concentration of the ion in the solution. So we can use colorimetry or UV visible spectroscopy to quantify this, to find the concentration of an unknown sample. How can we do this? And that was a long question in paper 3 in 2024 exam. The steps are, first of all, you need to prepare a series of a standard solution of non-concentration of the transition metal ion complex. So first prepare different concentrations and then use the spectroscopy, the visible spectroscopy or the colorimeter to measure the absorbance. And absorbance here is how much of the light was absorbed. Measure the absorbance of each concentration, and then you need to plot that the absorbance versus the concentration, or concentration versus absorbance, and this is called a calibration curve. That will give you a straight line, as you can see here, this blue line here. So it's a straight line between the absorbance and the concentration. Then you will measure the absorbance of the unknown sample, find the absorbance, and then find this curve to find the concentration of your unknown solution. This is how you find the concentration of an unknown solution of a complex ion or of a transition metal. Ligand substitution reaction. So one ligand can be replaced by another ligand. This is usually, as you can see here, a reversible reaction. So this is a reversible process. For example, you could have the aqua ion of the copper, which is surrounded by 6 molecules of water reacting with ammonia. That will give you this colored complex here, which is the copper with the 4 of the ammonia and 2 of the water, releasing 4 of the, or substituting 4 of the water molecules. With a chloride as well, you could have the copper with the water, and then that will, with 4 of the copper, that will give you the copper surrounded only by 4 of the chloride, because we know that chloride can only, we have the maximum of 4 ligands of the chloride because of their size, and they will replace the 6 ligands of water. Now the new complex has a different shape, because there is a change in the coordination number. Different ligands can form different strings bond. So ligand substitution is easily reversed, because you can see it's a reversible reaction here. However, there sometimes the new complex that is formed is more stable than the previous one. And this could be because one of two things. The first thing is the chelation effect. And chelation here is when bidentate, as we said, or multidentate ligand substitute monodentate ligands. And then there will be more stable complex, because there is an increase in the entropy of the system, because there are more number of particles as products. Or in case of the ligand forming a stronger bond with the metal. For example, when we have the iron 3 plus ion and cyanide, the cyanide can form a stronger bond with the iron than the water. So when you have the aqua ion of the iron 3 plus ion, and we have the cyanide, the complex formed here will be more stable. This is why the reaction will be pushed more. Hemoglobin inside our body is a complex ion as well, which is formed of a central atom or a central ion of iron 2 plus, and the iron 2 plus have around it six different coordinate bonds coming from 3 different ligands. 4 of these will come from the same molecule called the heme. One of these will come from another protein called globin, and then the sixth one will come either from oxygen or from water. So the iron can, or this complex, they can form this coordination bond with oxygen, or the oxygen can form a coordination bond with the iron or with the hemoglobin, and it can be transferred around the body. It will give the oxygen to the tissues, and then this is going to be substituted by the water molecules. However, when you have carbon monoxide, we know that carbon monoxide is poisonous, and the the reason why carbon monoxide is poisonous, because if you take carbon monoxide, then the carbon monoxide is able to make a coordination bond, which is much more stable than the coordination bond between the hemoglobin and the oxygen. And carbon monoxide will replace the oxygen and it will form carboxyhemoglobin, which is much more stable complex. So the oxygen cannot now bind to the iron or even the water. So this is why there's when you have carbon monoxide poisoning, you end up with suffocation because there isn't enough oxygen around your body. Variable oxidation states for the transition metal ions. So we know that transition metal ions exhibit multiple oxidation states. For example, manganese can have from +2 up to +7. Iron can have two of these, which are +2 and +3. The stability of these different ions will depend on the ligand, or the complex ions with these ions will depend on the ligand and the pH. So transition metals can act as catalysts. A catalyst will speed up a chemical reaction by providing an alternative reaction pathway with a lower activation energy. Transition metals are ideal catalysts because they have variable oxidation state and they can absorb reactants on their surface if they are in the solid form, and they can form complex ions with reactants in solution. There are two types of catalyst. The first one is called the heterogeneous catalyst. A heterogeneous catalyst is the catalyst that has a different phase than the reactant, meaning, or typically, it's when the catalyst is in a solid phase, while the reactants are either gaseous or they can be in solution. So how does it work as a heterogeneous catalyst or as a solid catalyst with a different phase of the reactant? There are three stages here for heterogeneous catalyst. The first one is the adsorption state. So the adsorption, the reactant molecule will bind to certain active sites on the metal surface, and then the reaction. So now the molecules of the reactants which had adsorbed on the surface of the catalyst, their bonds will be weakened and they can form new bonds to form the products. Once the products have been formed, the third stage takes place, which is the desorption, where the products leave the surface, freeing up the active sites. Some examples that you need to know from your specification are the use of the iron as a catalyst, which is a solid catalyst, in the Haber process, where the Haber process is a reaction between nitrogen and hydrogen to form ammonia. All of these are gaseous. So the catalyst here is iron. And also the contact process, which is the reaction between sulfur dioxide and oxygen to give sulfur trioxide. Well, vanadium 5 oxide is used in sulfuric acid manufacture. So we need the sulfur trioxide to dissolve it in water to give the sulfuric acid. Also, we have the hydrogenation of alkenes where we use nickel here, and that converts the carbon-carbon double bond into carbon-carbon single bond. Catalyst poisoning, we can see the catalyst poisoning in case of heterogeneous catalyst, where sometimes if we have some impurities in the reactants, they can actually bind to the active sites on the surface of the catalyst, and they will prevent the contact between or adsorption of the reactants on the surface of the catalyst. So this will reduce the catalyst efficiency and can stop the reaction. Example of that is in the Haber process. So sulfur, there will be sulfur impurities in the hydrogen gas. We also have the homogeneous catalysis at the second time, where this is when the catalyst is in the same phase as the reactant. So usually they are all in solution. So this process involves three different steps. The first one is when the catalyst form an intermediate species with one of the reactants, and then this intermediate will react with the other reactant to give the final product, and the catalyst is regenerated at the end. Two examples that you need to know in your specification. The first one is the use of iron 2 plus as a catalyst in the reaction between peroxide disulfate with the iodide. In this case, the peroxide disulfate and the iodide, they both have negative charge, they repel each other. So the activation energy for the reaction is very high, the reaction is very slow. The presence of the iron 2 plus and the ability to have two different oxidation states and that it can be oxidized into iron 3 plus, it will play a role in this reaction as a catalyst. So first it can collide with the peroxide sulfate and it will form a redox reaction. So peroxide sulfate, this one, with the iron 2 plus, that will give you the iron 3 plus. So the iron will be oxidized while the peroxidized sulfate will be reduced to give 2 of the sulfate ion. And then the iron 3 plus that is produced will now react with the iodide. So this is the intermediate that reacts with the iodide in the second step to give iodine, and then the catalyst is regenerated, which is the iron 2 plus. I didn't actually balance these equations, but you need to balance them in your exam. And this is the overall reaction for the process. And we also have the autocatalysis, where we use the manganese 2 plus as a catalyst, as a product in the reaction, and as a catalyst to for the redox reaction between ethane diuate and manganate to give carbon dioxide and manganese. So the reaction simply is that it starts with the manganate reacting with manganese 2 plus. So we have the manganate, MnO4. Also, I'm not gonna balance it now, MnO4, reacting with the manganese 2 plus, that will give the manganese 3 plus. And this is then we have this is an intermediate which is going to the manganese 3 plus, react now with the C2O4 2 minus to give the manganese 2 plus and also the carbon dioxide. So manganese 2 plus here is formed as one of the products in the reaction, and it uses the manganese that is generated will actually be autocatalyzed or become an autocatalyst because it catalyzes the reduction of the manganese. Metal equiions are complex ions formed when a metal ion is surrounded by water ligands. Something can you have something like iron 3 plus surrounded by 6 molecules of water, or the copper 2 plus surrounded by 6 molecules of water. The water molecules will form coordinate bond with the metal ions. So what are the properties of these metal ions? First of all, these metal ions are slightly acidic, and the acidity comes from the ability of these metal ions or the equiions to donate the protons from the water molecules from the ligand to the solution when they are dissolved in water to form three H3 plus H3O plus ions. So we have 3 plus metal ions and we have the 2 plus metal ions. The 3 plus metal ions are more acidic than the 2 plus metal ions. We are talking about the aqua ions here. And the reason why is because of the higher charge density for the 3 plus metal ions. So they polarize the OH bond in the water ligands or in the water molecules, and then weaken the bond between the oxygen and hydrogen, and they can donate the proton. So they can lose the proton more easily. Example of that, you can have the iron 3 plus aqua ion with 6 molecules of water. When you dissolve it in water, then it will start to donate one proton after the other to from three up to 3 different molecules from the water ligands to the water into the solution to give you this complex. This is the first one, and then it can have the second one with 2 hydroxides for water, where it donates 2 protons and then up to 3 protons. So the solution of the equiions of metal 3 plus ions are equiions are more acidic than the 2 plus. So what are the reactions of these aqua ions with different reagents? First of all, a reaction with hydroxide, it will undergo neutralization reaction because hydroxides are basic and the aqua ions are acidic. So when we have a small amount of the hydroxide ion, then these aqua ions, metal aqua ions, will act as an acid and they will donate the proton to the hydroxide, and then they're gonna form the insoluble, the hydroxide. So these insoluble hydroxides will have different colors depending on the aqua ion itself. And then in case of the 2 plus ions, or this is for both 2 plus or 3 plus ions, and it will do the same. So the 2 plus ions will donate 2 protons from 2 different molecules of water and will give you the hydroxide. You can either write the hydroxide like this, or you can write it as 2 of the water as a complex ion and 4 of the 2 of the hydroxide and 4 of the Ammonium hydroxide is amphoteric hydroxide, meaning it acts as an acid in presence of a base and act as a base in presence of an acid. So when you have aluminum hydroxide, which is a solid, it's insoluble, in presence of an excess of the hydroxide ion, it will give you this complex ion, which is soluble. So aluminum was 4 of the OH minus. So it will donate an extra proton to the hydroxide to give you the water molecule. In presence of an acid like H3O plus or simply as hydrogen plus, it will act now as an base, and it will take three protons from the acid, and it will form the aqua ion of the aluminium with 6 molecules of the water instead of having 3 hydroxide ions. So it will take 3 protons, add each of these to one of the hydroxide ion to form in total 6 molecules of water ligands surrounding the aluminium ion. And this is, of course, soluble. So when you start with the aluminum hydroxide, which is solid, with a base, excess base, or with an acid, in both cases, you will find that the soluble or the precipitate will dissolve. In case of ammonia, ammonia can act either as a base with the metal aqua ions, or sometimes it can act as a ligand. This is in presence of excess and specifically for copper. So as a base, it will act simply like hydroxide ion. So now what is going to happen is that the complex ion, complex aqua ion, react with the ammonia, will react as an acid, donate the protons to the ammonia to give the ammonium ion, and then form the insoluble hydroxide, which is going to be colored or maybe white if it's aluminium. In case of the transition metals, it's going to be colored complexes. In case of presence of ammonia as in excess, it will act as a ligand in case of the copper. So when you have a copper hydroxide, which was formed when you don't have excess, when you added ammonia dropwise, it's formed first, and then you have excess of the ammonia added, then there will be a new complex ion formed between the ammonia and water molecule. So it's going to substitute these hydroxides, and it will give you the copper with 4 of the ammonia, 2 of the water molecule, and this is going to be a deep blue solution. So the precipitate, when you add excess of the ammonia, will turn into a deep blue solution. Reaction of the metal aqua ions with the carbonate, we have 2 cases. The metal, which are 2 plus ions. So the 2 plus ions, aqua ions, when they react with the carbonate, they will give you the metal carbonate, which is going to be a precipitate. And in case of the 3 plus ions, because they are more acidic, so instead of making carbonate, the extra acid will react with the carbonate to give carbon dioxide and water. At the same time, what's going to be formed is the hydroxide. It's not going to form the carbonate, but will give you the hydroxide. So if you have the aqua ion of iron 3 plus ion and reacted with a carbonate, that will give you the hydroxides of the iron, and you can write it as FeOH3 and then H2O3, and this is going to be a precipitate, and this is in addition to the carbon dioxide and the water. In case of iron 2 plus, it will give you the iron carbonate. So this is with the iron 2 plus, it will give you iron carbonate, which both of these will be colored precipitate. So let's see the total of a summary of all of these reactions and these tests and what are the expected product or the expected observation. So if we have a testing with a hydroxide or ammonia dropwise, then with iron 2 plus, that will give us a green precipitate. The green precipitate would be the hydroxide of the iron 2 plus. And if you add excess of the hydroxide, there will be no change. So that will stay as a green precipitate. If you have excess of the ammonia, so after you add dropwise of the ammonia and give you a green precipitate, with the iron 2 plus, there will be no visible change as well, because the green precipitate will stay, which is the hydroxide. So the ammonia here with the iron will only act as a base. With the carbonate, there will be also a green precipitate, but the green precipitate now is due to the formation of the iron carbonate, not due to the iron hydroxide. With iron 3, so hydroxide or ammonia, that will give you brown precipitate of the hydroxides. If you add excess of the hydroxide, there will be no change. That is going to stay, so it's not amphoteric here. So it's going to stay as the hydroxide of the iron 3, so brown precipitate. Also, in excess of the ammonia will act just as a base, not to substitute the ligand. So you're still going to have the brown precipitate. And finally, with the carbonate, instead of having the iron carbonate, iron 3 carbonate, you're going to have the iron hydroxide and carbon dioxide gas. Copper 2 plus, this is a 2 plus ion. So with excess, with dropwise of the hydroxide or ammonia, it will form the hydroxides of the copper, and the hydroxide of the copper is blue, a precipitate. If you add excess of the hydroxide, there will be no change. You're still going to see the blue precipitate. But if you add excess of the ammonia, remember the ammonia will act as a ligand now to substitute the water molecules and will form this complex ion with 4 of the ammonia, 2 of the water, and the precipitate will dissolve and the solution will turn into deep blue. And finally, with the carbonate, it will give you the copper carbonate, which is blue-green precipitate. Finally, aluminum aqua ion, the aluminum aqua ion with hydroxide or ammonia, that will give you white precipitate of aluminum hydroxide. And if you add excess of the hydroxide, remember aluminum hydroxide that has been formed when you started to add the hydroxide will have an amphoteric property, so it will act as an acid. So the precipitate will dissolve to give you a colorless solution. So the colorless solution is due to the formation of the aluminum with OH minus 4 and 4. And then in case of excess of the ammonia, there will be no change. It will stay as a white precipitate of the aluminum hydroxide. And finally, with the carbonate, it will give you white precipitate of aluminum hydroxide, similarly like iron 3 plus, and also carbon dioxide gas. So